Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. We are looking at a series of lectures in computer architecture. In the previous lecture, we were looking at some of the basics of memory unit. We looked at some concepts of RAM, what goes into a static RAM and what goes into a dynamic RAM. So, this is what we looked at. So, what we will look at for today is a little bit more on the dynamic RAMs, and we will also look at how larger memories are constructed using the basic blocks that we have, some smaller devices that we have, and we will also look at some of the different read only memories that are used. So, let us look at dynamic RAM, a quick recap on what a dynamic RAM is in the first place. So, dynamic RAM, it does not retain the state indefinitely, therefore, it has to be refreshed periodically. So, remember that a dynamic RAM essentially is each dynamic RAM cell consists of just a simple capacitor and a transistor. So, data is stored by storing it as a charge on the capacitor, and since the charge is likely to dissipate, so we need to keep on refreshing the charge periodically, only then we will make sure that the content is retained. Okay. So, let us look at the basic structure that we have. So, we said that the data is essentially stored as a cell array and addressed by means of specifying a row address separately and a column address separately. The row addresses and the column addresses are essentially multiplexed on the same address lines. Therefore, we first send the row address, latch it using a row address signal, then send the column address, latch it using the column address signal. Once both have been latched, the row decoder and the column address decoder will decode the lines, and you will select the particular row and column that we are looking at, and then the data is read through the sense and write circuits, read or written through the sense write circuit. So, this is what we have. In order to have a fast mode of operation, we also have something called a page mode operation here, where you can specify the row address first, and then without having to repeat the row address, just by changing the column addresses, you can read out the consecutive locations that are there, that are stored in a particular row. So, this is something that we have. There are other faster modes of operations that have been developed, where you are also using some kind of a synchronization with the help of a clock. If you look at the previous asynchronous DRAM structures, you will find that there is nothing called a clock that is used anywhere over here. Okay? But later devices, we will find that nowadays we use what are called as synchronous DRAMs. In the synchronous DRAMs, what we do is we also use a clock signal, that is, the operation of the memory is synchronized with the help of the processor clock signal. So, you have a clock signal that is given over here in addition to the RAS, the CAS and the read write and the chip select signals that are given, that are used. Okay. So, we have a separate control unit which is responsible for the timing and the control. So, that takes clock as the input. Okay. So, if you look at the overall structure now, you can see that there are some additional things that we have shown. We have shown a row address latch, a row decoder which goes to the cell array, and a column address counter. Okay, see that what we are talking about is a column address counter and then a column decoder, and then which connects up to the read writes and circuits and latches. Now, in addition to that, we are showing certain input register and certain output register that we have here. Okay, so let us look at how this particular organization is used for effective access of data. Okay. So, you will see that the output of these sense circuits are connected to a latch. Okay. So, during a read operation, what actually happens is that the contents of the cells in a row are loaded onto the latches, and during a refresh operation, okay, remember what we have as a refresh operation. Refresh is used because we need to periodically refresh, and for that we have something called a refresh counter that is used. Okay. So, if you look at this, the refresh counter will generate successive row addresses. So, when successive row addresses are generated by the refresh counter, successive rows will be selected by means of the row decoders, and when the row address is selected, that particular entire row, all the cells in that particular row will be refreshed automatically. Okay. So, what we do is, therefore, when we want to refresh, we do not allow the refresh to change the output that is there in the data registers. So during the refresh operation, the contents of the cells are refreshed without changing the contents of the latches. Okay, so these latches that we have here, the write circuits and the latches that we have here and the data output register that we have here, these will not be affected by means of this refresh operation that takes place. Okay. So, we kind of provide some kind of isolation between this and the refresh operation that is done here, because remember that when you are doing a refresh operation, essentially you are selecting that particular row. So, when you select that row, then the data that is there in that row should not change the data that is there in your latches or in the output registers. So, for that we have these registers which are latched only when a read operation is done and not when a refresh operation is carried out. Okay. And you can see that the operation is directly synchronized with the processor clock signal. So, with the help of this clock plus all this additional counters that we have, okay, for the row address and for the column address, we can have a very effective design for the synchronous DRAMs. Now, with the help of the synchronous DRAM, we can also support that fast page mode kind of an operation that we talked about earlier. So, we normally refer to that as a burst mode of operation. That is, normally what we do is that the data held in the latches will correspond to the selected columns, okay, and they will be transferred to the output. When you want to do a burst mode of operation, so what we do is successive columns are selected using the column address counter and the clock. So, you see that we have something called a column address counter over here. For the refresh operation, row addresses have to be generated consecutively. Okay. So, for that we have a refresh counter which will generate row addresses one after the other. Now, for this kind of an operation where I want to access all the columns which are there within a particular row, so I only select the row address and all the columns that are there will be accessed by means of this column address counter. So, remember that a counter will count, right. So, it will generate all the successive column addresses. So, when I use this successive column addresses, I can access all the columns one after the other, successive columns one after the other, okay, and that can be directly used to select a particular row and a column, and the data can be accessed from there and stored in the latches. Okay. So, that is, a cache signal need not be generated externally and a new data is placed during the rising edge of the clock. Okay. This is what we have with respect to these kind of a synchronous DRAM which also support a burst mode of operation. Okay. An additional thing which is done on SDRAMs in order to improve the rate at which you are able to read data from the DRAMs is what is called as a double data rate synchronous DRAM. Okay, this is something that we use in our current PCs that we use today. Okay, so DDR SDRAM. So DDR stands for double data rate SDRAMs. So where the cell array is basically organized into two banks and the two banks are accessed during a clock cycle, and during the rising edge of the clock one set of bank is accessed, and during the trailing edge of the clock or the falling edge of the clock another bank is accessed. So, now what will happen is within one clock cycle you are able to access two banks, therefore twice the amount of data that is to be accessed, that can be accessed. So, we are essentially increasing the amount of data that can be transferred in 1 second. So, what is it that we are actually increasing? We are increasing what is called as the memory bandwidth. So, memory bandwidth is normally defined as the number of bits or bytes that can be transferred in 1 second. Okay. So, by going in for a double data rate SDRAM, because I have organized into two banks and I access both the banks in one clock cycle, you can double the rate, the bandwidth that you have, rate at which the data can be accessed from the SDRAM. Okay. So, these are devices that we use in today's PCs. Okay. Another thing we need to look at is the memory latency, which is the time it takes to transfer a word of data to or from memory. Okay. Both these are terms that we normally use, latency and bandwidth, and latency is determined by the technology that is used for the DRAM, and bandwidth by these kind of organizational improvements and by you going in for techniques such as using double data rate SDRAMs. Okay. Now let us look at, once we have these devices, these small devices, say a 512K by 8 device or a 1 megabit by 8 device, there is one device which can store about 1 megabyte of data. Using these kind of devices, how do I actually construct larger memories? So, if you look at today, when we talk of physical memory today, we talk about 2 GB RAM or 4 GB RAM or 16 GB RAM, okay? We talk about these large devices. So, does this entire 16 GB or whatever we talk about, does it come as one single device, that is one single chip, or is it multiple chips organized together? Often you will find that it is multiple chips that are organized together to form a larger memory. Let us look at how this kind of an organization takes place. Okay. We will take an example. Let us say we want to implement a memory unit, okay, of 2 megawords of 32 bits each. Okay. That is, I want to have a full memory unit which has 2 megawords in it of 32 bits each. So, this each word is 32 bits. Okay. Now, this I want to do using 512 by 8 static memory chips. So, let us assume that we are doing a static memory organization here. The same kind of structure will be used for a dynamic memory also. Okay. So, we will just use for illustration purposes, I am talking about using static memories. So, let us say we have 512 by 8 static memory chips. Using 512 by 8 static memory chips, we want to construct a memory which has 2 megawords of 32 bits each. Okay. So, let us see how this can be done. You can see that the organization that is given over here. So, what is it we are using? Just look at this. I have 512 by 8 memory devices that I am using, and I want to construct 2 megawords of 32 bits each. So, because since I have 32 bits each, for each word I will require 4 devices. Okay. So, which is what you can see here. In a given row there are 4 devices used. So, I will get 512 by 32 as the amount of data that I can get from each row, if I put it like this. Okay. So, given a particular address, the same address is applied to each of these. Okay. You will find that I will get 512 into 32 is the amount of memory I can get from each row. Now, how much I want? I want 2 megawords of memory. Okay. 2 meg, if I divide by 512, you will see that you will need 4 such 512 address devices. So, I organize this into rows. Okay. So, and how many columns will I have? I have 4 columns and I have 4 rows. Each row we already said will have 4 chips because of the to accommodate for the 32 bits. So, each chip essentially is implementing 1 byte position. And how many rows we have? We have 4 rows. Each row will correspond to one 512 block. So, 512 0 to 512 will be in this row, 512 to 1024 will be in this row, 1024 to the next 512 will be here, the last 512 bytes will be here. So, together we will be able to get the 2 meg memory that we want. So, 2 meg memory organized using 16 devices of 512 by 8. Okay. So, total memory required is 2 megawords of 32 bits each, and now I am getting that organized using 16 such memory chips. Each memory is 512 by 8. Okay. So, this is the organization that we have. So, now that I have put all these devices over here, how do I actually interconnect them? Okay. So, if you look at this, the address lines that we get, how many address lines do we have? I have 2 meg words. So, 2 meg words would mean that I have 21 address lines. So, address lines are, they go from A0 to A20. Okay, 21 address lines starting from A0. So, I go up to A20. Okay. So, these 21 address lines you will see are connected to these different devices. Now, remember that these are all 512 capacity devices. So, for 512 capacity device, I only require 19 address lines. So, 19 address lines, the lower order 19 address lines A0 to A18 will connect to each of these devices, and which row is going to be selected, that will be determined by the most significant 2 bits over here, which is A19 and A20. Okay. So, using this I will put it through a 2-bit decoder and select one of these 4 rows. So, once these 4 rows get selected, then a particular byte within the 4 bytes that are there within that particular row can be accessed. So, this is how the structure is designed. Okay. We will take a short break and then come back and continue with the lecture today. Welcome back after the break. We were just looking at how the larger memory structures are constructed using the smaller devices. A quick recap of that before we continue with the next topic. So, as we said, our goal was to construct a 2 meg by 32 bit memory using 512 by 8 chips. So, 512 by 8 chips, we saw that this can be done with a 4x4 organization. And how do we select a particular chip? A particular chip is selected based on the higher order address bits, that is A19 and A20. 2 bits are used to select one of these 4 rows. You can see what is happening over here. If A19 and A20 are both 00, that means my addresses are basically going from 0 to A18, right. So, it will be addressing the lower addresses, that is from 0000 to 000 or to all the way up to A18 to A0 being ones. Okay. So, that will correspond to these 4, the memory that is there, the data that is there in these 4 devices. Okay. There is this particular row. So, if 00 is the input over here, that is A19, A20 are 00. So, this particular row gets selected, and the addresses that I have are the first 0 to 512 words that you have here. Okay. Or you can look at it as 2 meg words that we have, the first 512 words. So, that will be what will be stored over here. So, that we are able to access by using this kind of a decoding of the higher order bits. So, when this is 0 1, the next row will get selected. When it is 1 0, the next row will get selected. When it is 1 1, the topmost 512 words will be selected. So, that is all we are saying is the 2 meg words are selected into 4 blocks. Lowest 512, next 512, next 512 and next 512. So, which of those gets selected is determined based on this higher order 2 bits that you have here. Okay. So, using these kind of decoders, external decoders, okay, you can make sure that the devices get selected appropriately. Now, for each of these devices, okay, how many address lines are going to each of these devices? We saw 19 address lines will go. This is what is inside. Inside this essentially is 19-bit address is given and an 8-bit data, either input or output. Okay. And the chip selects will have to be given for each of these devices when that particular row is being selected. Okay. So, with this kind of an organization, you can build larger and larger circuits. Okay. Now, what do we do with respect to dynamic memories? It is also actually a very similar organization. Okay. So, when we want to build large dynamic memory systems, okay, so they are also done with the help of these kind of organization. That is, you use smaller DRAM devices and construct these larger memory systems using these smaller DRAM devices. Okay. But the only problem is when we use a DRAM, and since we are talking about 1 gigabyte, 2 gigabyte or 16 gigabyte, 64 gigabyte and so on, the amount of space that this will occupy on your motherboard, okay, when you are constructing a PC can become very large. What we actually do when we use dynamic memories is that we use a particular packaging structure which is called as SIMs, which are called as single inline memory modules. Okay. And another structure called DIMMs, which is a dual inline memory module. In fact, if you buy a dynamic RAM from a store now, you will find that it actually comes in SIMs or DIMMs. That is, you will find that it is one kind of a package that actually comes. Okay, and the memory modules basically are, this itself will be like a small board. Okay, and these memory modules will be organized on this small board. Okay, so the memory modules are actually assembly of memory chips on a small board, which will plug vertically onto a single socket on the motherboard. That is, on the motherboard you will not find this kind of a structure, but this structure will be there on some smaller board, and that small board will be actually going into a socket. Okay. So, that is the how it will be organized. This will occupy very less space on the motherboard, and if you want to expand it, you can always remove one SIM and place a SIM with a larger capacity. So, using the same socket that is available, you can expand the size of the memory that we have. So, this is practically how these dynamic memory devices are plugged into the motherboards today. Now, we talked about, when we are using a dynamic memory, we also talked about the memory controller that is required, right. So, what are the jobs to be done by the memory controller typically? Remember that we have to reduce the number of pins, we use multiplexed addresses. That is, we first select the row and then we select the column. So, higher order address bits will select a row in an array, and they are provided first and latched using the RAS signal, and then the lower order addresses will be provided to select the column, and they are latched using the CAS signal. Okay. So, this generation of the RAS and CAS will normally be done by the memory controller. Okay. Because why do I need a memory controller to do this? Because what a processor will actually do is, a processor will issue all the address bits at the same time. This multiplexing of those address lines into row address and column address is normally done by the memory controller circuit. So, this memory controller circuit is the one which will take care of doing all this generation. Okay. So, the controller device that we talk about, this memory controller could be either on the motherboard, or it may come packaged along with the memory device. Okay. So, there are both kind of operations that we have. So, you can see, so this memory controller will be the one that will interface to the processor on one side, take the address from here and then generate row address, column address, etc., which will interact with the memory device that you have. Okay. This is a broad picture of how the memory controller will look like. We will take a look at another type of memory device, which is the read only memory device. So far we looked at random access memory devices, which is RAM. Now we will take a look at read-only memory devices. Now why do we need these read-only memory devices? The static RAM and the dynamic RAMs that we looked at, okay, they are volatile devices. Okay, what do we mean by volatile? Remember we said that if you turn off the power, it will lose the contents. So therefore, if you want an application where you want the data to be stored in the memory devices even after you have turned off the power, then we need a different kind of a device. Okay, SRAMs and DRAMs will not suit that purpose. So we want non-volatile devices. So one example of non-volatile devices, okay, are what are called as read-only memories. We will look at how these read-only memories are used. Which are the applications which will require such kind of read-only memories? You will see that for instance the operating system, okay, you may want to, the moment the computer is turned on, the operating system has to be loaded from the disk into memory. Now to load it from the disk to memory, you will need some instructions. So where will these instructions be? These instructions typically will be in some read-only memory, so that the moment you turn the power on, instructions will be taken from this read-only memory or ROM, and this will give instructions to load the OS from the disk into the onto the physical memory. Okay, then the OS will take over and it will run. Okay. So at least for this initial booting purposes, we need these devices called ROMs. Okay, read-only memories are required. Okay. Now these are non-volatile memory devices. Now why do I want them to be read-only? That is because I may not want to write into them. I just have stored some data into them and I just want to keep on reading that data. Okay. So that is the purpose for which we use these read-only memories. Okay. Okay. So now how do we actually, now obviously some data must have been written into them. So how is that writing normally done? The writing is normally done by means of some separate process. Okay. So but the reading of the memory will be done the way we do it for a normal RAM or a volatile memory as such. Okay. So normal operation for reading, whereas separate writing process, okay, writing is done separately. Some other mechanism is used to store the data into the memory devices. Once it is stored, reading can be done just as we do for a normal device. That is, you will specify an address, give a read signal and the data from that can be read. Okay. That is what we will do in this case of read-only memories. Okay. And how do we write into this into these devices? So writing is done in a number of ways. One is we have a plain read-only. In fact, there are different types of read-only memories depending on the way the data is written and so on. Okay. So one is the plain read-only memory ROM, these are the original devices, where the data is written into when the device is manufactured. So right at the time of manufacture, these the data that you want to go into this ROM is written. Okay. Later we've had devices which are programmable read-only memories or PROM devices. Okay. Now in a programmable read-only memory, the what we allow here is that the data can be loaded by the user, okay, but once it is loaded, it cannot be changed. Okay. So the process of inserting the data is irreversible. Okay. So storing information which is specific to a user in a ROM is expensive. So you provide some kind of a programming capability, so that, which is why you call it as a programmable read-only memory. Okay. So you can program the data that goes into this, but once it is programmed, you cannot change it. These are called as programmable read-only memory devices. Then we have another category of devices which are called as erasable programmable read-only memory. Okay. So here it is basically a programmable read-only memory, but it is also erasable in the sense that by using some different technology, you can erase the entire data that has been stored there and then you can program it with new data. Okay. But again, this kind of an erasure is not done directly when the system is powered on, but you typically remove the device from the socket and then use some kind of an ultraviolet rays or some specific technology is used to erase it, and then you can program it using some specific program what are called as EEPROM programmers, and then you can program it with the data and put it and start using it as a ROM device. Okay. So the stored data is erased and new data can be loaded. This obviously gives us some flexibility. Okay. This is useful during the development phase of digital systems because you will be designing something, you may want to make some changes and then again try it with this. So in those cases we go for these kind of erasable programmable ROMs. Okay. And normally, as I said, the erasure is normally done by exposing the ROM to some ultraviolet rays. Another category of ROM devices is what is called as electrically erasable programmable read-only memory, the EEPROMs as these are referred to. Now, we saw that the EEPROMs are erased only when you expose them to UV light, okay, some ultraviolet light. So, here what we do is in electrically erasable PROMs, this can be erased under the control of some electrical signals itself, okay. So, we do not need really ultraviolet light. Instead, these devices, the EEPROMs, okay, they can be erased by sending some specific electrical signals. Normally, they are the electrical signals that are used are slightly higher voltage than the normal voltage used for the normal mode of operation, and without removing the socket from, without removing the device from the socket, even as it is connected to the circuitry itself, you can erase it and you can program it, okay. But once you programmed it, it will retain it. It is a non-volatile memory, okay. So, it will retain the data even if you switch off the power, but you have the capability to reprogram this. So, these are called as EEPROMs. The other type of read-only memories that we use very much today, okay, are what are called as the flash memory. So, here this has an approach which is similar to EEPROM, okay, but what this will allow you to do is, you typically read the contents of a single cell, but normally the writing is done in entire block of cells, okay. So, you can write to a full block of memory and you can read the contents of the individual cells, okay. These flash memories, these are used in most of our devices today. These flash devices, they have much greater capacity, okay, and lower storage cost per bit. In the evolution of ROMs, the flash memories are used as the devices these days. So, to summarize what we have looked at today, basically on synchronous DRAMs, that is the use of clock signal in the DRAMs and how we are able to achieve faster modes of data transfer and operation using these SDRAMs. Okay. So, we also looked at construction of larger memory units using smaller devices, okay, how using the smaller devices, how we use additional decoders, address decoders and construct these larger devices. And then we looked at different types of read-only memories. So, we looked at the basic PROM, the programmable read-only memory, EEPROM, EEPROM and the flash memories. So, basically we have looked at RAMs and ROMs. So, that is what we have covered so far. Okay. So, the questions to look at what we have covered so far. Question number 1, what is a synchronous DRAM? Question number 2, how does an SDRAM function? Question number 3, what is the purpose of a refresh counter in SDRAM? Question number 4, why are ROMs required? Question number 5, what are the characteristics of the different types of ROM devices? Thank you.